Hi folks, we are on Unit 4, Day 6, and we're going to look at how to take derivatives from first principles. So this is going to be a continuation of what you guys did a lot of in the Advanced Functions course, in particular when you were estimating that instantaneous rate of change. So all of those questions where you were finding rate of change of a function, all of the different functions you looked at last year, and estimating it, we're going to use what we've done so far with limits to find a better, more consistent way of finding that instantaneous rate of change. And that's going to be our derivative, which is a big focus of the next couple units. So just to kind of review, in the advanced functions, we talked about the difference between average rate of change and instantaneous rate of change. Remember that the average rate of change in an interval is really just the slope of that secant line. So we just do delta y over delta x. And there's a visual of that here we're looking at the slope of the secant line between 2 points on our function. So that is the average rate of change between this x value here and this x value here. And the slope of that line is that ARC, or average rate of change. The difference between average and instantaneous is, of course, the fact that with instantaneous, we're not looking at the slope of a secant line, but instead we want to estimate the slope of a tangent line. Now, the instantaneous rate of change is the exact rate of change of a function at a specific value. So average rate of change is over an interval of x values, and instantaneous is at one certain x value. You want to find the slope of the tangent at that point. So in advanced functions, you guys would have looked at the different ways, preceding intervals, following intervals, or the one that's kind of balanced right around, to figure out what the slope of the secant approached as the intervals got smaller and smaller. So you maybe would have done like between, say, 1 and 2, and then 1 to 1.1, and then 1 to 1.01, and 1 to 1.001, and kind of squished that that delta x interval down smaller and smaller. And then just to kind of compare, we go from looking at the graph of a secant line, which is between two separate points, and you want to kind of squish this second point in closer and closer to that first point. And as the second point kind of gets squished closer and closer, we get closer to getting the slope of the tangent line, which is that red one. So these secant lines, if you kind of move them closer and closer and closer, we end up getting the slope of the tangent. Of course, we couldn't have the delta x be actually equal to 0, even though that was kind of what we wanted, right? We did very small, you guys would have done very small delta x values, like 0.001, I think often would be what you would have used, because we wanted to get it as tight as possible in there to get a really good estimate for that instantaneous rate of change. So this will look familiar from the Advanced Functions course. We have the value of the function at a plus h. And in advanced functions, I think most of you guys would have done this as just like let h equal 0.001. So in MCV4U, you would have said let h equal 0.001. And you would have had something like, for instance, you might have had IRC equals, and you might have kind of said F at, maybe it was 4.001 minus F at 4 over 0.001. And that's kind of what you did last year in the Advanced Functions course. This time, now if we're looking at this and kind of trying to figure out how to get this really small value to estimate that instantaneous rate of change, we have a new thing in our toolbox. We know that there's actually a mathematical skill that we have that means make something get really, really close together. And what that is the limits that we've been talking about for the past few lessons. So instead of just saying, let's just call h, what's a really little number? 0.001. Sure, that's pretty small. And put it in there. What we really want to talk about is what happens as h gets arbitrarily small. So closer and closer and closer to 0. We know it can't equal 0 because we're dividing by it, but we want to get it really close. And that is the limit. So what we're going to do now that we know limits, we can find the slope of the tangent, or the IRC, the instantaneous rate of change, by taking the limit as h approaches 0 of this same difference quotient that you guys used all the way through advanced functions last year. So it's the same thing, but instead of just plugging in 0.001, now we're going to say, let's be a little bit more mathematically rigorous about this, and let's take the limit as h is getting close to 0 of that function. Okay, so again, the different interpretations of this is that what we end up with this difference quotient as we get closer and closer to 0 with that h value is that gives us the slope of the tangent to the graph at that point. We can also interpret that as the instantaneous rate of change at that point. So depending whether we're talking about a graphical representation, so knowing what the slope of the tangent is doing can really help us when we were sketching graphs, and knowing what the instantaneous rate of change is can really help us when we're solving problems involving some kind of real life situation. So these mean the same thing, but kind of depending, are we talking about a graphical interpretation, or are we looking at how some function of a real life situation is changing? Those are the two big interpretations there. So let's give this a try. We're going to define this. This is a really important thing, that the limit as h approaches 0 of that difference quotient is the derivative. So the derivative is one of, I would say, like the two biggest ideas in calculus, and that's what the whole rest of our course is going to focus on. This is going to talk about how a rate of change is related to a function, and how the rate of change is going to be changing over the course of the function. So we can find out an awful lot about a function, whether we're talking about its graph or kind of behavior of a real life situation, by knowing how it's changing. And being able to find this derivative is going to be a pretty powerful thing. Different notation for this, and if you guys watched that video that was linked in the earlier introduction to this unit with the Newton and Leibniz kind of calculus controversy, Newton denoted this f prime of a, and Leibniz used this notation dy dx. So this means the difference in y divided by the difference in x. So the change in y over the change in x. So it looks kind of similar to, say, a delta y over delta x, but using the d instead of the delta indicates that it's an instantaneous change instead of the change over an interval. So that's kind of reminiscent of delta y over delta x being like our slope formula from grade 9. And this f prime notation, they each kind of have their pros and cons for sure. The Leibniz notation is a little bit more descriptive in terms of the rate of change of y in terms of x, which will come into play when we have functions with more than one variable that might be changing. And this notation, Newton's notation, is kind of handy because it is linked to function notation, and we're able to be descriptive about what the x value is. So pros and cons of each, but you need to be able to use those pretty interchangeably because you will see both notations. So here's again our definition. This is super important that you need to have this memorized. It's really just the limit of that difference quotient from advanced functions. So it's the same thing you would have used in advanced functions, but now we're just taking the limit as h approaches 0 rather than just calling it, let's use some little number for h. We're going to be a bit more mathematically rigorous there and say that we need to take the limit as h approaches 0. So let's try this with an example. So we want to find the derivative of f at x equals x squared at x equals 2. So we are looking, and because I have function notation here, I'm going to use Newton's notation. So I'm looking for f prime at 2, and that is the limit as h approaches 0 of f at 2 plus h minus f at 2 over h. So that's just using that limit definition of the derivative. And now I'm going to sub in the things that I know. So I need to keep my limit notation. So the limit as h approaches 0, I obviously cannot sub in 0 here. I would get an indeterminate limit. So I'm going to have to do some math. F at 2 plus h is 2 plus h all squared. And then f at 2, of course, would be 2 squared, which will be 4. And divide that out by h. Now I'm going to FOIL out on top. So I get the limit as h approaches 0 and just kind of simplify and hope things work out well. So here I get 4 plus 4h plus h squared minus 4 over h, which is kind of nice. That minus 4 disappears, and on the top now I can factor. I still need to keep my limit because I haven't taken the limit yet. I'm going to factor that numerator and call it h times h plus 4 over h. And then again, of course, that can reduce, and now I've gotten rid of what's giving me that indeterminate form. If I reduce out those h's, so now I have the limit as h approaches 0, now I just have h plus 4. So that's something that I can take the limit of, and it won't be indeterminate. So it's at this point that I drop my limit notation and just say sub in 0, so 0 plus 4 is 4. So that tells us that the slope of the tangent to y equals x squared at x equals 2 is 4. And you guys could have done that using the difference quotient, right? And it would have been actually probably faster if you had just kind of said, okay, what's 4.001 squared minus 4? If you put in, 2.001 squared minus 2 squared over 0.001. So in advanced functions, so what you would have done is said that IRC equals 2.001 squared minus 2 squared over 0.001, and you would have plugged that into your calculator and said, oh, it's about 4. So this way looks longer. It really does, and it is. The one thing that the big advantage that this has is that it gives an exact value. And this one was really just an estimate. It's not actually the instantaneous rate of change. It's just the slope of a secant line where the 2 points are very, very close, but it's not the slope of a tangent. We're just doing an estimate. So we would estimate, and this is actual. But you may be looking at kind of the amount of work between the two, and obviously this does not feel very efficient, and it's not. The big advantage that this method will have, though, is that we're going to be able to find a function or an equation that will represent the instantaneous rate of change for all x values. And then it's quite a lot easier that we are going to actually just find this derivative one time, and then we'll be able to use it over and over. Whereas the old way, not only was it just an estimate, but if, say, you wanted to know the IRC at x equals 3, you'd have to redo it right from scratch. So here we're going to we want to find the derivative of this function at any point, any arbitrary point. So I'm going to say that the derivative of this function, so f prime at x, will be the limit as h approaches 0 of f at x plus h minus f at x over h. So this is the limit of the difference quotient. And I'm not going to use x equals 2 or x equals 3. I'm just going to leave it as an x. It's a little bit longer to do this once, but then we'll be able to use it and have kind of a general form with any value. So here f at x plus h is x plus h squared minus f at x is x squared over h. And obviously I would get an indeterminate form if I subbed in. I've got a 0 on the bottom, so I can't put that h in. So the limit as h approaches 0, FOIL this top piece out, x squared plus 2xh plus h squared minus x squared all over h. So now you'll see this is looking a little bit reminiscent of the previous one where we had x equals 2. So we still have the limit as h approaches 0. Now we have 2xh plus h squared. I'm going to common factor out an h, and I get 2x plus h over h. And of course now we can reduce the h's, which gets rid of my indeterminate form if I had subbed in. So I have the limit as h approaches 0 of 2x plus h. Now I can sub in and drop the limit notation, so I get 2x plus 0 or just 2x. So this tells me that for the function f at x equals x squared, the derivative or the slope of the tangent at any point is just 2x. So that's going to be really handy. So we know that that was true for x equals 2, the derivative was 4, but now we can find what's the slope of the tangent when x equals 150. It's 2 times 150, so it's 300. Or at x equals -3. It's 2 times -3, so it's -6. You can just find the derivative of any point because now we have a general equation for it. And we're going to be able to do that for a lot of functions. So this process here is called taking the derivative from first principles, and it gives us a general equation or function that will tell us what the slope of that tangent is or what that instantaneous rate of change is at any point. Okay. Once we have that, we know that f prime, so for this function f at x equals x squared, f prime at x is equal to 2x. So if you wanted to find the derivative at 0 or 2 or -3, you just use this new equation that we've come up with that represents that instantaneous rate of change. So f prime at 0 is 2 times 0. So the slope of the tangent at x equals 0 is 0, which should make sense, right? That's the vertex of the parabola, so that would have a horizontal slope. F prime at 2, we did that one already, the long way. So it would be 2 times 2, which is 4, which is what we got. F prime at -3, we just take the 2, multiply it by the -3, and that would have a slope of -6. Okay, again, you can kind of sketch out the graph of the parabola and see, do these slopes make sense? We're going to talk a lot more about that later in the unit.